Hi, this is Logan Honeycutt, and this is my Quideo. First, we're going to talk about the basic question. And the basic question was a Gallup poll that had 1,785 adults that were asked if they went to a church or synagogue in the past week. And 40% of those adults said yes. So our first question was, p-hat is the proportion of people who did attend. So what's the mean of the sampling distribution of p-hat, and what's the standard deviation? Well, first, just for my peace of mind, I found p-hat, which is the 714. That's 40% of the sampling of the adults. And then the mean of the sampling distribution would be that 40%, that 0.4 would be the mean. And then the standard deviation, I just did that normal formula right there. And this is our normal formula, and this is where I just plugged everything in. I did our p, and then I did our 1 minus our p, which would be 0.6. And then I did divided by the n, which is like all the adults that were asked, or the sample, and then I square rooted all of that to get 0.01159, which I later round to 0.0116. So then question B, it says, explain why you use the formula for standard deviation. Well, I used that formula for standard deviation right there. Because of rule of thumb 1, which is the total U.S. adults population size is at least 10 times larger than the sample population, which was 1785. And so since it is 10 times larger, it's that quote-unquote normal or approximately normal, which lets us use that standard deviation formula. Next, it just asked to check that we can use normal approximation, and we can because of the rule of thumb 2, which is NP and N times 1 minus P, and I just did those right there. So this is N, and then this is P and 1 minus P, and then this is what I got for those two, and they're both bigger than 10, so you can use normal approximation. The last question for our basic question is probability that p-hat takes place between 0.37 and 0.43, and will and SRS of 1785 usually give a result between the maximum or minimum 3% points of the true population. So it's basically like asking how valid is this, like is it going to be close to the true population, or is it going to be kind of off? And so this is my formula I used. I just kind of like wrote it out saying that this is going to be the lower and this is going to be the upper, and then I did my normal formulas here, and then that's what I got when I did those, and then my calculator, and then so this would be the percentage that I would get from those. This is like the negative amount, and this is the positive amount, and if you put those in the z table, that is the percentage or your confidence interval that comes out. And so I basically came to the conclusion that over 99% of all p-values should be within that plus or minus 3% points from the true value. So whatever you get, like whatever sample amount you get, that's going to be fairly close to the true population of all U.S. adults. So it's going to be a good representation. Next is going to be our advanced question. And this question was about tire wear research. And they researched tire wear in 2 different ways. One was by the weight of the tire, and one was by the wear in the grooves. And they had a random sample size of 16, and they provided a table for us, which is right here. And this was just like the tire number, and then this is the weight of the tire, the amount of wear that was in the groove, and then the difference between those two. Just kind of giving you your different measurements that you would need to answer the questions. So, our first question was what's the 95% confidence interval for the mean differences in the 2 methods? So I just stated that it is a sample of 1. There's only 1 sample, and it's a t-test. And here's the little formula you would use. And then you can see that the T star is going to end up being 2.131. You just get that 16, which is your sample size, minus 1 is 15, and you just look that up in your book, and it's 2.131. And then the standard deviation, and obviously this is the sample size again, and the standard deviation you would get just by doing some basic math with the table. And then this is your mean that you would also get by doing basic math with the table. And so then you plug that all into this formula, and you end up getting your max and your min, because you have that plus and minus right there. So our max would be 6.2743, and our min would be 2.8369. So the differences are going to be in between there, like that range. So yeah. And part B just asked us to convince or give convincing evidence that there's a difference in the methods. So with research, they want to find like what's the best one to use when you're researching. And so basically they want to say like what's the difference between the two, and would there be a difference, or can they use both, or should they use just one? And I said yes, there is a difference. We are 95% confident that the true difference between the two methods is between those two numbers we got in part A. And since that's larger than 0, and the 95% confidence is significant evidence, because that is like very confident that there is a difference, that there would be a difference no matter what you did, no matter how many you sampled, no matter how many you continue to sample, no matter what, there's always going to be a difference between those two methods. The last one from my Quideo today is the AP question. And this question was about golf balls. Here's the question. There's a lot of extra information in there, so I just underlined the basic, like what you would need to know. That there's the 5 standards that the ball has to meet. It can't exceed the 291.2 yards distance. And they want to get as close to that traveling distance as possible without exceeding it. And the standard deviation is 2.8 yards. And they'll like have this new process that they want to use, so you're kind of like doing the math for that. So the first question was, what's the probability the ball will go too far? And 288 yards being the mean. So x equal distance ball travels in my equation. So if x is larger than that 291.2 that it isn't supposed to exceed, if it like actually does exceed that, that would be your equation. And so you're trying to find the z-score, but since that z needs to be larger, this is your like regular formula that you would use, which is the mean, and then this is the amount that the ball is going to be, and then this is standard deviation. And then doing all of that, you get 1.14. But since you do need that z-score to be bigger, you're going to get that normal z-score for the 1.14, and then 1 minus that. And so then it'd be this really tiny number right here, though 0.1271 would be your probability. Alright, next one. What's the probability a ball will go farther than 291.2 yards? It's literally the same question, but at the same time, it's different. So, this one's going to be binomial. So this is going to be the one distance, and this is going to be all 5 distances, because in the problem, it does ask, like, it's going to test 5 balls, so it needs to be the probability of those 5. So, since you do have 5, you're going to exponent to 5. But this is your regular 1, and so you're going to do 1 minus that one, and then you're going to exponent to 5, so then you get 0.5068, and then you 1 minus that, and you get 0.4932. So that is the probability that a ball would go farther than 291.2 yards out of those 5 distances that would be tested. And then the last one is, when are you 99% certain that a ball won't exceed the 291.2 yards, but it's the largest mean that can be used. So it wants to be like almost 100% certain that the ball won't exceed that yardage, but it wants to be the largest mean that it can be used. So the z-score of 99% is 2.33. So you use that in your problem, because normally you would try to find the z-score, but now you're trying to find the mean. So you're going to do the little z-score over here, and then put in your standard deviation and your other mean, like the yardage that it can't exceed. And then you're going to basically like try to figure out this. So you would first times 2.33 times 2.8, and then you would minus 291.2, and then you would divide by -1 to get rid of that negative sign, and then you would get 284.676. And that would be like the highest mean that can be used, but it won't exceed 291.2 yards. So yeah, there's my Quideo.